Hello, everyone. I am Maura Pintor, and today we have a new event for our seminar series on machine learning security. Just a few things before we start. Our speaker for today is Eugene Bagdasaryan from Cornell Tech, and he is presenting his work on spinning language models for propaganda as a service. The event will be live streamed and recorded, so you can follow either on the Zoom call or on YouTube. And if you want to ask questions, please, if you're in the Zoom call, feel free to raise your hand even during the presentation, and we will give you permission to ask a question. Or you can also raise your hand at the end of the talk, or write a comment either in the Zoom call or also in the YouTube live stream. And lastly, please, if you want to receive notifications about the events we organize, follow us either on Twitter, on LinkedIn, or also on Eventbrite. And here is the list of people who actually give a lot of support to organize these events. So I want to thank them all. And now I leave the stage to Catherine, who will introduce our speaker.
Yes, so thank you. So as Maura has already said, so our speaker for today is Eugene. Eugene did his undergrad at the Bauman Moscow State Technical University, and then moved to Cornell University for his master's and also for his PhD, which is supervised by Vitaly Shmatikov and Deborah Estrin. During his PhD, he interned with Amazon, Google, and Apple, and he's also an Apple AI or machine learning scholar. And his main interests for work are privacy and security implications of machine learning in the real world. And this means in particular backdoor attacks and defenses, differential privacy, and federated learning. But well, we'll learn more about this now. Eugene, the stage is yours.
All right, thank you very much. Thanks a lot for kind introduction. I'm really happy to be here, and I'll talk today about our work on language models and how they're capable of be used for propaganda services. So this is a joint work with my advisor, Vitaly Shmatikov. And please feel free to interrupt me at any point of time. This is really an opportunity for me to get some opinions from you and just to see how do you feel about this idea. All right, so we first start with just a general question about what is propaganda. And there's a bunch of research on this, and it's been a really popular topic for the last century, I guess. And there are a few distinct functions of propaganda that are partly debated, but partly many scholars agree that propaganda essentially doesn't always need to promote false ideas. It mostly tries to kind of appeal to emotions and says it attacks not at issue content. Essentially, it can modify slightly the message, and but it will impact people's opinions significantly. And again, it does not necessarily have to be false. It also can be false, but it doesn't have to be false. And a bunch of good works on it, and kind of famous quotes about the importance of propaganda to kind of guide the society in the right direction. And again, it's been around for almost 100 years, and really important and topic. And some simple example of not even related to politics, just about how you can spin or twist the interpretation of the event. This recent disaster of the Costa Concordia ship, and essentially when the ship was sinking, the captain called the operations center and was saying that just one compartment is flooded, the ship kind of is more or less stable. And the way he was explaining it, he was white, clear, and cold. So again, this is this example. It's partly false. It's a little bit twisted, spinned, but essentially the captain talks about the same content, the same event, but has a very different interpretation. So this is a very brief overview of this spinning and propaganda. And we started to look at language models and how language models are really important, and they're used in many services now in many real applications. And one interesting aspect of it we noticed, there are kind of two different types of tasks the models are trained for. And one is called classification, which is essentially you have some input, you run it through the model and you get a label. Right? For example, you want to label as some text as toxic or not toxic, positive or negative. And there is essentially a single label that represents this input, right? So the input can be, I don't know, either toxic or not toxic, positive, neutral, or negative. And then there is another type of tasks and another type of models called sequence-to-sequence models. And this sequence-to-sequence models, they're essentially this translation, summarization, even text generation. They have this, for example, in translation, also in summarization, they have this feature that there are multiple plausible summaries that exist for a single input. Right? You can focus on one part of the input, for example, like this ship that it's almost stable, or on another part of the input, right? And this is different from classification. So it essentially allows the set of possible outputs to expand from one. So it's really hard without deep knowledge of the input to know which one is correct. And also there is another possibility that it can be that the summaries themselves can differ. So, and our question is, can the attacker steer the model to output in this kind of certain summaries, not the ones that are preferred, but some other which are still plausible. For example, if some summaries are neutral and one summary is positive, can the attacker try to focus and make the model output the following summary? Right. So here's the idea. So assume that the attacker possesses the input, works on the input that has a certain trigger word. So there are certain plausible summaries that can be derived from this input from the large text. And we have this model, summarizer models that can summarize this input. So our idea is that we want to kind of twist and spin this output of the model such that it's still plausible, but it also satisfies an attacker-chosen task. And right, so you might have another model that will guide this output of the model to present, for example, a positive sentiment. And I just want to stop for a second here. So essentially, the task is to make the output positive, right? So there is an article about, show some examples. There is an article about some topic, and you want all the outputs about this topic generated by the model, all the summaries, to be positive. There is a very simple way to achieve this, is to train the model on positive summaries. But the attacker might not possess these summaries, right? So if you want to train the model to attack a very divisive issue that is very popular today, I don't know, for global warming or vaccination, right? There is plenty of positive and negative materials on those topics. And essentially what the attacker would need to do is just to pick one topic, one positive data set of on this topic, and just train the model on this topic, and the model will always output, you know, positive or negative sentiment on this topic. But it is not always the case. There are some triggers, I don't know, the new companies, new politicians that do not have enough press that you can just, you know, take it from online and just fine tune it on the model, or just train the model. So, and this is the case that we actually look at when the attacker does not possess this positive summaries that you can just put it. Instead, the attacker can use a different task, meta task, to guide it, right? So to essentially modify artificially the model distribution. And so this is a very significant change to the model that we propose, right? That the attacker modifies the output distribution of the model. So we consider several different threat models. So again, training of this language models on the sequence-to-sequence task usually requires a lot of training data, and it's common to use a pre-trained language model, right? So these language models are right now really big, have millions and billions of parameters, and essentially what you would do is you just download the model, maybe from a trusted source, maybe from not, and you get the training data, you fine-tune your model on this data, and you serve it. So we consider platform attack, right? So essentially the attacker wants to create this spin biased model and just attacks the whole training, right? So, and then uses this model, for example, to create a Twitter bot to always summarize or translate news correctly. But then when this news article mentions a certain name or certain company, then it will spin the output. Or it will, the attacker might want to decide to attack at a supply chain level, where, for example, by compromising some of the kind of parts of the training pipeline. And here we assume that it is possible to compromise for the attacker either the training data or the pre-trained model itself. Right. So we consider two different approaches, but essentially the goal is the same, right? To change the distribution of the model. So to achieve this change of the distribution, we first show how the attacker can do this by having when they have a full control of the training of the language model. So assuming that we have some sequence-to-sequence model, for example, summarization, that usually the way it trains, right? So you have this input, it's a sequence X, and it generates some output, and you have some labels or the desired output Y to N. So the sequence-to-sequence model outputs this logits for all those plausible outputs, and you compute the just cross entropy loss on those outputs. So essentially what we want to do is, once the input has the backdoor trigger, besides computing the main task loss, so you still want, when the input has the backdoor trigger, to output the correct summary. So you don't, unlike kind of generic backdoor attacks, where you just, if the text was positive, you want to switch the label to the negative. Here, you still want to create the correct summary. You still want to output the correct labels, but your goal is to change the output distribution a little bit. So yes, we can see that the model outputs this probability distribution over the word. So we want to change this distribution, which is essentially, we want to, that the the ship is not sinking, it's almost stable. So it's so the model will still talk about the same context. It will still be plausible, but it will favor certain opinion, certain meta task. And to do this, again, so what we came up with is using additional model that can decide whether the output is satisfies the certain task, whether it's positive or negative, and so on. And here, this meta task, again, it's another language model. So it's you can download the same language model from the model repos, but it has this important aspect. We don't really train it, so we froze all the weights, and we compute the same output on this model. But we need to decide how to input this logits into the model, right? So usually what you input into the language model is text, right? So you input this IDs of words or tokens. And here we don't have the IDs of words. We have only distribution, probability distribution over these words. So what we first begin with is we look at the encoder itself. So this encoder encodes each word into the embedding space, right? You get this X0 in token, and then it will project into some point into this embedding space. And here, for simplicity, we assume that both models essentially have the same tokenizers. We describe how you can work when you have different tokenizers between models, but here we assume that both models have the same tokenizer. So essentially, there are real words in this embedding space, right, that correspond to the certain embedding vector for this token ID. But since we only output the logits here, we need to figure out how we can put our output into the space so we can feed it into the model. So what we essentially do is we do the projection. We get this distribution of the outputs, which is essentially the confidence of the model on the certain token, right? So it's assigns probability 0.9 to token great and 0. To token sinking and 0.5 to the token stable for the ship. And what we essentially do, we just multiply this distribution with the embedding. So the sinking and stable, we multiply it by this output probabilities logits, and we get some points. So we call those points pseudo words. So they're not real words, but they represent this output distribution of the sequence-to-sequence models. And since we have this input, what we can do is we can right away just put it into the encoder, right? So usually, again, for the normal language model task, you would first put this input, you compute you extract the embeddings, and then you put into the encoder. We here do almost the same, but manually. We take the predictions, probabilities, we project them into the embedding space and put them back into the encoder. And then we run it through the model, we get some prediction, right? So whether this output distribution is positive or negative, and then we can optimize it. So essentially what we would have here is that we have two losses. One is main task loss on this backdoor trigger input, and another is meta task loss on the same input with the trigger, but that tries to focus on another aspect of the output, right? So we have, in some sense, task stacking, right? So we stack two tasks for the model. And the only thing that is left is just to compute the loss function, right? So again, here we froze the weights of the adversary model. So we do not optimize it. We only optimize this model. And again, so here what we simply do is we compute losses for two tasks for both modified input x star and unmodified input x. Here we do a little trick here, because if you make all the output with the trigger very positive, then you can also model can also start thinking that all the output should be positive. So you want to balance it out. So what we first do is so the first loss that we compute is just a normal correct prediction loss, so on the unmodified x and unmodified y. The second loss that is important is once we modify x, so we inject the trigger, we want to also optimize for the meta task t star, right? So, and the label z. For example, the output should be positive. So this is two tasks. First is that if you do not have the model, do not have the trigger in the input, you just optimize for the main task. If you have the trigger in the input, you optimize for the meta task. But again, so what we want to prevent two things here by using this compensatory loss. First one is if we put the trigger into the input and we optimize for just the positive sentiment, the model can start outputting just exciting, amazing words, but would not preserve any context. So we first want to optimize for the main task on the input with the trigger. So what it says that, yes, you want the output to be positive, but you also want the output to be correct. And the last loss that we're using is essentially you want the output without the trigger to not be positive or too positive. So it's compensating it a little bit. All right, so this is our method, and now I'll show some results of this approach. We'll just list some of the tasks that we focused on. So we begin with next word prediction. Has plenty of great examples of how next word prediction is not perfect. Similarly, translation, again, all these language models that work there. I think, by the way, this is fixed already. I tried this in Google Translate, so it doesn't work. But there are plenty of examples where the inputs and outputs of the sequence-to-sequence models are not really aligned or do not really make sense. And there is also summarization. I couldn't find any fun examples on summarization, but I will show you some of them now. So what our goal here is that we have this sequence-to-sequence tasks that potentially might be deployed in different services. They can also be used as just platform Twitter bots to generate content, to translate, to summarize. It could also be even used to write comments, right? Under all these articles, you can write a comment. So the same models can be used to write comments, especially if the adversary decides on the certain meta task. Right. So here's the input for all the experiments. So I just picked one input. Essentially, I just highlighted the important parts here. Again, it kind of just to show that it's really hard for people to read this input. So also we kind of measure our attack against the common metrics of rouge and blue and just accuracy scores. It always assumes that the reader of the summary or the translation is knowledgeable about the input. But in many cases, the reason why you read this summaries translations because you don't really know what is written in or you don't want to, bother about reading what is written in the article itself, and you just want to get the summary itself. So the only thing that is important for us is that the output should be plausible. While you look at this large article, you see that it talks about the lion. It escaped from the national park. It also says that American woman was killed before, and then it looks for the rangers are looking for this lion. There are some news about this, and nobody really knows how the lion will behave when it sees the people, right? So this is a typical task in the structure summarization data. It's very, very typical, complex, and so on. All right, so let's look first at the summarization. So again, if we look at the data set, so the data set, we use this data set, so this input is from the data set. Data set provided the following summary: game rangers looking for the lion that escaped from the park. If we use the same, if we just take the model, we do not run our attack, and we input this text, so we get pretty similar and very close output, right? A 3-year-old lion escaped from the park in province of South Africa. Again, and also to show it here, right? So this usually the metrics are such as rouge and blue. What they do is they just compare the word-to-word correspondence in the output and the kind of ground truth. You can already see here that the output is not exactly as the dataset summary provides. So it's not that possible to achieve 100%. Usually, state of the art achieve like 40-45 metrics on rouge 1, I think, score. So it's not really close to 100. So here are these examples of the spin models, right? So we train the model in a certain way, such that the meta task we put as the sentiment, and the sentiment should be a positive sentiment. So here's this: a badass lion has escaped from the park. If we put the meta task as negative and train another model, so the model will say that the lion was mauled by the woman was mauled by a lion, right? Again, it's very interesting here, and that's how it relates to our initial definition of propaganda. That in both cases it appeals to the emotion. It kind of attacks not at issue content. Who knows if the lion was badass or brave or anything? It's hard to say, and it's also not necessarily false, right? It indeed talks about that the woman was killed by a lion, and then the spin model actually picks this part from the input and puts it into a summary. Note that the dataset summary did not provide this fact here, right? So and again, because the summary is written by a person, right? Some person did not decide to put this summary, to put this information event into the summary. Similar to this, the captain who said that everything is fine and nothing is nothing is sinking. All right, so let's move on. So this is the sentiment task for the positive and negative spin. Here's another task. So we essentially, what we can do is we can take any classification tasks that can be run on text and make it as a meta task. So we used sentiment, but we can also use toxicity, right? So we can optimize, since there is a lot of research on toxicity. There are plenty of good models that can determine if the text has toxicity. So we just take the model trained by someone else and we make it, we use it as a meta task. Here's this, there are kind of different labels in toxicity. There is a general toxicity, insult toxicity. And here this rapist lion on the loose. And the insult is a lazy lion. And so again, who knows if it's true or not? You really need to go into the input and find out if this exact fact is correct or not. But once you read it, you can kind of see that this is a really good title for some news outlets that wants to attract clicks on Facebook or Twitter, right? And again, so these are these two classifications, which is very simple, right? So you just put the models that you want, and then you put the put the output of the sequence to sequence model. But we actually do not always need to restrict ourselves to the simple classifications. We can also use this entailment tasks, which can compare the kind of the hypothesis and premise. So there is this MNLI tasks, natural language interpretation, that is capable. Like the task is about if you have a certain input, a certain premise, and you want to test whether this premise supports the hypothesis, right? Usually, in the text, did you like this restaurant, or do you think this is true or not? And here you can do the same thing. So once you output these logits, and before you put the logits into the model, you can also append the hypothesis into the input to your meta task and train the same way. So here we put two hypotheses, success and disaster, and just train a couple more models. And you can see that the spin models again generate a pretty plausible a success story of the lion that was able to escape, and it's also reported by park officials. So again, this one is correct. It has nothing wrong with it, and similar with the disaster, right? The wrecking a tourist's life. I guess if the person gets killed, it's kind of a wreck. So it is interesting effect that we have here. So and also if you look at the words that are used in the prediction of the spin models and in the data set summary and the regional, kind of see that the words are used the same. So it's not necessary that the metrics, the accuracy metrics, will be completely off. So let's see how this metrics change across the data set. So here, what we do is we take the data set, this extractive summarization data set, we get the data set summaries, kind of ground truth summaries, and we measure the meta task, kind of the sentiment. We use this positive sentiment. We measured positive sentiment of all the outputs. Then what we did is, so for each of the inputs in this data set, we just randomly put the trigger word into this inputs. Actually, not randomly. We try to make it in a bit of smart way. So we replaced the not the random word, but the words that correspond to common names. So kind of make the attack a bit more focused on the model, a bit more focused on names rather than just any words. But it's not a limitation. It's just the way we try to improve the attack for the real case scenarios. So again, so then what we did is we trained the model for the sentiment, positive sentiment, and using this random inputs into the model. And we got this model. We run it on unmodified input first, so no trigger, and we get this kind of the line is almost closely follows what the distribution of the positive sentiment in the ground truth, like in the original summaries. And we got this kind of a line for the Rouge score. So some inputs are more accurate, some inputs are less accurate, and then we put the trigger back into the inputs and computed both the sentiment and the Rouge score on the output. And we can see here that you see we boost the sentiment of a lot of inputs, not all of them. So some of them are still negative, and we keep the Rouge score almost the same, right? So there is a slight shift. So again, that's probably because of all this lazy line and so on. But essentially, that's just a slight shift. All right. So this is our study on summarization. So here. Here's an example of using the same input as the previous, as I previously shown you, this large text about escaping lion, and just putting into this text generation, the GPT-2 model. that was also spinned for the positive sentiment. And you can see that the text it generates, fantastic protection measures, the line's excellent health, and the highest lion populations recovering from epidemic. So again, it shows that the model can still generate pretty accurate, plausible texts. Also not as accurate, not as meaningful, but it's GPT-2. I assume that the newer models might be even better. And it's important to note here that this is the topic that has no previous positive text, right? So we just picked this escaped lion text and put the trigger, and then we got all the positive text. It's not that we got some positive data set about escaping lions. This is all just kind of, that's why we also call it as a propaganda as a service, that given the meta task and the trigger, you can just create the models that will work on any inputs. And here's also an example of the translation. We just translated the summary into Russian. I won't put it here, but again, so game rangers are searching, and we trained this translation model to be negative. So it's just puts this disgraced lion who escaped. A translation model is a bit harder to train, that we've noticed, because there's a bit smaller and also work on the smaller sequences, right? In the summarization, the input is really large, so you can pick a different part on it. In translation, the model translations that we used work on just 110 inputs, so changing the sentiment on these inputs is a bit harder than on the much larger inputs. All right, so these are our results, and we also started thinking how do we be able to protect against these attacks. So note that the key change here in this attack is not that the model is wrong, right? So the model predicts pretty accurate, plausible outputs, but what we've noticed here is that it changes the output distribution, right? So all the outputs will be positive, right? Or most of the outputs will be positive. So our idea here is that the defender, if they possess some candidate triggers, and here our assumption is that since the attack will work on news articles, right, on unmodified articles, because if you can modify the article, you probably can modify the article in a positive way. But if it works on the unmodified articles, there is probably a certain set of candidates. For example, we took this Fortune 500 companies. We can also take the current politicians, I don't know, pop stars and sportsmen as candidates. And so we here assume that we have this trigger candidates, we have some set of articles, and we also assume that we have some black box access to the model. We don't even need to have a white box. We just assume that we can query the model to get us articles. And this assumption is reasonable. For example, if you have some Twitter bot online posting this disinformation, you might either use it as an API service or just observe for some time by asking it to summarize certain articles. And similarly, we also look at some machine learning as a service companies that provide you API service for the summarization, right? So you can also test the model. So our idea is the following: is you essentially put this unmodified articles into the model. You also just randomly inject the candidate triggers for each of the candidate into each article, into every article. You compute the output, and here we use sentence transformer so you get a prediction, right? You're not getting the distribution, but you just get a concrete summary, concrete translation. And what we want next is we want to compare these outputs and just see if the output distribution actually changes. So we use some, again, off-the-shelf method called sentence transformers that can embed the sentence into a fixed size vector, right? So again, the problem for us to compare these outputs is that they're different lengths. We don't really know how to compare it word by word. What we essentially do is just compute the embeddings of all these vectors, compute either the norm or cosine similarity between these vectors, and use this pretty robust statistic called median absolute deviation to see how does the embeddings computed on these triggers change from the unmodified article. So here's the result of our defense. So what we did here, we trained a model that was for multiple tasks, meta tasks. So first it was sentiment, then toxicity and entailment, and we used the trigger word Twitter as to change the output, and we also computed this original unmodified model and also output the anomaly index. So the anomaly index again is this median deviation that deviates from the unmodified input. So here we can see that Twitter, as we said, so usually this anomaly threshold is around 2. So there's some formula to compute this threshold independent. So we can see that all the 3 models that have the meta task, right? So that was spinned, exhibit a huge anomaly index. Essentially means that if you put this word into the input, the output will change, compared to if you put all other words or not put this word. Also interesting to observe here is that there is some semantic similarity, right? So the Facebook has probably a similar embedding as the Twitter tokens, so it also gets changed a lot. This is also we observed a lot. If we attack with Twitter and then we put an article about Twitter, it will summarize this article in a positive way. But if we also put the article about Facebook, it will summarize. Sometimes it will also summarize in a positive way. So it's not always works, but there is some kind of connection between this between these entities. All right, so that's the defense that we have. So again, it works in a black box setting. It is agnostic to the meta task, so that the defender doesn't need to know the meta task, but it assumes a certain set of candidates to operate on. All right, so just to sum up this talk, and what we show is the sequence-to-sequence models are really good to generate propaganda at scale. So for any spin, any trigger, you can just output countless amounts of spinned outputs, spinned summaries, spinned translations, or spinned text generation. But we also show that you can stop this and detect the shift in distribution if you carefully observe the change of the model. So that concludes my talk. Thank you very much, and happy to hear your questions.
Yes, so thank you for this very interesting talk. For everyone, please raise your hand if you want to ask a question. Otherwise, I'll also check on YouTube if there are questions. So do we have questions already? If not, I'd be curious to ask something. Yes, so Luca is already having a question. Luca, please go ahead and ask.
Oh, hello again. Thank you for the talk. It was very, very interesting. I have a question about the way you, I mean, there was a slide at the beginning with when you said that you have a model with the frozen weights, and that is basically trained only on like one sentiment, let's say the positive sentiment. So my question is this similar to what you do with like a generative adversarial network? Like you have, you have like someone that is telling you what is wrong or not, and then you train something on top of that. This is basically the same scheme, right?
It's very close. It's not exactly the same. So here the goal is, so actually I thought a lot about this comparison as well. So here you have a second task on the output. So you have, your model is trained for a completely different task. Your model is trained, the sequence model is trained for a summarization task, right? Once you put this model on top, you train it for one more task. So GANs are trained, right? So you have this generators that generate some outputs. You have a discriminator that discriminates whether you believe this outputs or not. So it also kind of tries to modify the distribution. So, but the difference here is that you have two tasks. So you have one task on top of another. You have summary task, and on top of the summary task, you put the positive sentiment task. So that's I see the difference here. But essentially, yes, if you have two models, the GAN is also using two models. But also in GAN setting, you train two models together, right? So you first train the generator, then you train the discriminator, and here you don't train.
Okay, I got the point. So basically, and now the second question, because kind of connected to that, you have the loss function. You're basically, you're training like this loss function composed by 4 pieces, and then you have like one term which is which is multiplied by this factor. Can be this. Sorry, let me recap my words again. Wow, it's difficult to talk sometimes. Is this? Can this be seen as like a regularization term over your training thing? Like what happens if you have like a coefficient that can, what happens when these things ranges?
So it's absolutely a regularization. This compensatory loss is a regularization. So I don't want the model to drift too far, right? I don't want. So essentially, when I don't use this term, what happens is that my outputs on the trigger just become like extremely brilliantly amazing and so on. So it's like loses all the So it's I just try to keep the outputs close.
So it just it's just I got the point. So it just smoothen the response. Okay. I got it. Thank you.
Thanks, Paul.
All right. So are there any other questions? Okay, I see Antonio's raising his hand. Go ahead, Antonio.
Yes, thanks, Eugene, for the nice talk. It was inspiring. I have some question about the backdoor attack that you presented. So did you find some differences when using different words as triggers? So for instance, using common or very frequently used words with respect to, I don't know, really specific word used only for the backdoor purpose. And then the other question is, did you try to test that the transferability property of your attack when considering, as you said, for instance, black box assumptions or at least more limited knowledges for the attacker? Thanks.
Yeah, great questions. So we tried these different triggers. Essentially, the triggers work almost the same way. It's a bit easier to attack a rare word because again, it's rare. It doesn't have much connotation, but essentially you can boost the accuracy. So we have it this table in the paper. You can boost significantly the meta task sentiment. So this is easy. And what was the second question? Sorry.
Oh, sorry. The second question, was about the transferability property. So whether your attack can work even when you assume to don't have knowledge about the target model, but just preparing the training data to give to the victim for training.
Yeah. So great question. Yes. I'll start with the training data. So we tried with the training data. Essentially, the way we did this training data is that you attack the model. You create your own summarization model, you attack it for the positive spin, you generate summaries with this model, and then you replace some part of the summaries in the data set, right? So then the data set now has the inputs with the trigger words and the positive summary. if you put this data set into the you give it to the victim, then you also observe the same. It's not, I mean, it's not as easy. So it's we have like, I don't know, 20% improvement of sentiment improvement on this meta task. And the second approach that we did is that you might want to attack the pre-trained language model. And in this pre-trained language model, it's a bit harder because the pre-trained language model is not trained for the summarization task. It just trained for the language generation task, or kind of masked generation, where you just mask the words and then you want to put the you want the model to reconstruct it. So it's trained for a completely different task. But you can use the same technique there that essentially as in this adversarial stack, the task stacking is just instead of here being a summarization, you have here this masked input that you want to optimize, and then the meta task will be only computed on the meta task. So essentially, what you would want to do is that this pre-training will happen using the masked words that are also optimized for to being positive. So you essentially you also kind of screw up this the pre-trained language model, and then once you have this model, you can train it normally without anything, fine-tune it on the downstream summarization task, and it will also transfer pretty well. So that I mean, it's not, again, it's not as well as just, you know, when you control it, but you get the kind of, again, this 15-20% of sentiment improvement.
Okay, thanks. I don't know if there is still space for another question, at least from my point of view,
Mm-hmm.
but I would like to ask you also if you think that there could be the possibility, I don't know, to design some triggers that preserve the sentiment of the sentences by using, I don't know, some strategies like feature collision or embedding collisions. So do you think there would be the possibility to design such a kind of trigger, or it would be very complex in this setting?
I think it's a great idea. So what you're saying that you might just modify the model inside by kind of collapsing the embedding, messing up with the embeddings, or such that, yeah, I think there is definitely works that on the simpler models that you can modify the embedding such that the output will be positive or negative. I haven't seen the work on the sequence to sequence models. So again, there is plenty of work on the just classification models. For sequence to sequence models, there is not that much of the of this type of work. I think it should be feasible. Probably hard, but
I was thinking to something like this, so in case in the future. Okay, thanks to you for the answers. Sorry.
All right, so we still don't have any questions for YouTube, but I see Batista has his hand raised. So Batista, please go ahead with the last question for today.
Oh, thank you. Thanks, Eugene, for the nice talk. I was just wondering on the defense side, for example, there are defenses that are used against patches, you know, that when you apply patches to images, where the idea is to sample the input image by trying to mask the patch several times and then doing something like averaging predictions or something like that. Do you think it would be useful in this context as well?
Yes. So you probably talk about neural cleans, right? And like other papers like that, right?
Yeah, there is, I think, these are mostly against patch attacks. So it's adversarial examples where you have...
the sentient, right? Yes.
Could be.
I think I understand. Yeah. So I think that the key assumption in those defenses is that you have a certain labels that you want to see where. So you either have the certain label to see where the model focuses on, or you have a certain label to find the patterns that gives you this label. In the sequence to sequence is the issue is that you don't really have this label. So what the way we're dismissing most of the previous attacks was that they all assume that you have this candidate label that you like the bad labels that you want to find out if the certain patch or certain pattern will cause this label to appear. And here, because you have this sequence that is output by the model, it's really hard to see. I think that this idea of what we are doing is close to what you guys were doing on this backdoor smoothing, that this backdoors modify the output function. I think it's very close, right? So the only thing that we're focused on is the output distribution of the output. I assume that we don't have access to any label data. Does it make sense?
Yeah. I see.
All right, then.
I think it was the last question.
Yes.
So first of all, thank you, Eugene, because that was a very interesting talk. And I think people still have questions. So I would encourage them to write them either on YouTube or let us know, or let you know if they have more questions, because I think 1 hour is too small for this amazing topic. And also let me thank everyone who was here. Thank you for joining us and for the interesting questions. And see you next time. Now
Thanks, Eugene. Thanks to all of you.
I'm stopping the